So in this lecture, we're going to talk about the pigeonhole principle and some applications of it. This is section 6.2 in the book. So the pigeonhole principle has to do with taking a set and dividing it up into, partitioning it into subsets, and then saying something about, if I know how many elements are in the original set, can I say something about the sizes of the sets in the partition? So the original kind of mnemonic for the pigeonhole principle is, let's say we have pigeons, we have pigeonholes, and the pigeons are all going to fly over here and make a nest and do whatever it is pigeons do in their spare time. And so the idea is, if I have more pigeons than I have holes, so here I have, I think, 7 pigeons and 4 holes. If I have more pigeons than pigeonholes, then at least one of the holes is going to have more than one pigeon in it, right? So maybe this one goes here, and then this one goes here, this one goes here, this one goes here, and the last 3 are going to have to double up somewhere, right? So if I have more pigeons than pigeonholes, at least one of the holes is going to have more than one pigeon in it, right? Completely trivial, right? Completely obvious, but sometimes a very useful thing to kind of deduce facts. And if you look in the exercises in section 6.2, you see a lot of kind of practical applications of the pigeonhole principle. It's a very simple idea, but with some powerful consequences. Right? So let's make it a little more formal. So we have a set of in objects, in elements. We're going to partition it into k classes. So maybe we could just say subsets instead of classes here, but it's usually kind of more intuitive to talk about partitioning objects into classes, because if we're talking about people, we break them up into groups. It's a little more kind of rolls off the tongue more easily to say classes than subsets of people. Right? So if I have more objects than I have classes, then at least one of the classes has to have 2 things in it. Okay, so the proof is to take a set with n objects, and we partition it. So take this A that is n objects and split it up into these sets A1, A2, A3. And here the union with the dot in it means that the sets are pairwise disjoint. So I'm partitioning it. A1 and A2 don't have anything in common. A1 and A3 don't have anything in common, etc. Okay? So if we assume that each thing in the class has at most one element in it, then we could say n is equal to the cardinality of A, which is the sum of the cardinalities of the subsets, because it's a disjoint union. All the elements in A are accounted for once and only once over here. And if each of these classes has at most one thing in it, then this is less than or equal to 1 plus 1 plus, the total number of classes, which is k. Okay? And now if n is greater than k, this part gives us a contradiction. So, if I can partition A this way into classes, then the number of classes has to be greater than or equal to the number of elements. Okay? So by contraposition, if the number of elements is greater than the number of classes, then at least one class has to have 2 elements in it. Okay? There's a more general phenomenon here. If I take, this is more interesting, if I take n objects and I partition the n objects into k classes, and if n is greater than pk, where p is any positive integer, then one class has to have at least p plus 1 elements in it. So you've probably seen this kind of thing, this kind of argument before in the like an old riddle. So you're getting ready for work and the power goes out, and you know you have 3 different colors of socks in your sock drawer, but they're not paired. So how many socks do you need to grab in order to guarantee, so you can't see the socks because the power is out, how many socks do you need to grab in order to be guaranteed that you have at least 2 of the same color? That's this type of argument right here. Okay? So here P would be 1, and we look at it 2, that's the exact pigeonhole principle. Right, but if I have n objects and I break them into k classes, and n is greater than p times k, at least one of the classes has to have p plus 1 elements in it. Again, this is the same kind of proof. To take A, split it up into k classes. If each class has at most p things in it, then I have n equals the number of things in A, which is the number of things in the classes. This less than or equal to p plus p plus p, because each of these classes has at most p things in it, and they're k classes, so altogether have at most pk things. So by contraposition, if n is greater than pk, then I cannot do this, right? I can't split A up into k classes that have at most p things in them. At least one of them is going to have p plus 1 or more things in it. Okay? So, just one of the exercises from the book is to see how we apply this. What is the minimum number of students, each of whom comes from one of the 50 U.S. states, who must be enrolled in a university to guarantee that there are at least 100 students from the same state? Okay? So that's a question that is answerable by the thing on the previous page. So what I'd like to do in this case is imagine the worst case scenario. So we're looking for the minimum number of students that we have to have enrolled to guarantee that there are at least 100 from the same state. So the worst case scenario is to have 99 from each of the 50 states, right? So if I have 99 from each of the 50 states, then, well, I don't have 100 from the same state, right? So, but if I have one more than this, right? So if I have 99 times 50, it's possible for me to have this many students without having 100 from the same state, because I could just have 99 from each of the states, and then I don't have 100 from any state. But if I have one more student, now I have to have at least 100 from one of the states. Again, it's the exact same computation from the previous page. So let's say k equals 50. So A1 is the set of students from Alabama, and A2 is the set of students from Alaska, and A3 is the set of students from Arkansas. And so each of the 50 sets consists of the students enrolled from that state. And if I have 99 times 50 plus 1 students, then it's not possible for all of the classes to have at most 99. At least one of them has to have 100. Right? So, for me, the easiest thing to think about is you want at least 100 in each class. So the worst possible way to fail that is to have exactly 99 in each class. So 99 times the number of classes. It's possible for me to have this many without 100 in any given class, but if I add one more, then if I have this many students, I have to have at least 100 from one state. So this problem is a little bit more interesting. This is also out of the book. I think this is number 23 from section 6.2. We have 24 girls and 24 boys seated around a circular table. There's always one person both of whose neighbors are boys. Right? So we're going to take a circular table, put some people around it. 25 of the people are boys, 25 are girls. And I want to know, there's at least one person such that both of the people sitting next to them are boys. Okay? There's at least one person having that property. So let's prove this. Okay? So, well, so I'm going to say NP is number of boys sitting next to person number P. Right? So I have my people, I number them arbitrarily, 1, 2, 3, up to 50. So I have 50 people, 25 boys, 25 girls, so P is going to go from 1 to 50, and NP is the number of boys sitting next to person number P. NP is either 0 or 1 or 2. Right? So if I look at person number P, if they're sitting in between two girls, then NP is 0. If they're sitting in between a boy and a girl, then NP is 1. If they're sitting between two boys, then NP is 2. Our goal is to show that there is at least one person such that NP equals 2. That's what it means for them to be sitting between two boys. Both of their neighbors are boys. So I want to know that NP is 2 for at least one of them. So we want to assume NP is less than or equal to 1 for all P. So each person is sitting next to at most one boy. And we're going to get a contradiction here. So let's note that if we add up all the NPs, we get 50, because if I go around the table and count the number of boys that each person is sitting next to and add them all together, that's going to count all of the boys exactly twice. So I have 25 boys. This counts all the boys exactly twice. It's going to count each boy once for the person on the right and once for the person on their left. Right? So I get 2 times the number of boys. So if NP is less than or equal to 1 for all P, and the sum of the NPs is 50, then NP equals 1 for all P. Okay? If they're each less than or equal to 1, and there are 50 of them, and they add up to 50, then none of them can be 0. Right? So I have zeros and ones here, add them up and get 50, and there are at most 50 things here. I can't have any zeros. Right? So that means that everybody has to be sitting next to at least one boy, and so here we have assumed that everybody's sitting next to at most one boy. So here, everybody's sitting next to exactly one boy. Right? So now what I'm going to do is I'm going to go around the table. So I have the table, and I'm going to split it up into chunks. Okay? So those circles, those are where groups of boys are sitting. So the circle means that there are only boys in the circle, and then I split where there are girls. Right? So I kind of break the table up into the circles are where one or more boys are sitting, and in between the circles are where I have one or more girls. Okay? So I'm kind of splitting things up where the girls are sitting. And now, so each circle contains one or two boys. Obviously, it can't contain three or more boys, because if I have three or more boys sitting consecutively, there's one boy somewhere in there who has boys on both sides. Right? And that would be an NP equals 2 for that boy. Right? So each of these circles can have one boy or two boys, but not more. Okay? So now let's think about what has to happen in between the circles. Right? So there's somebody sitting right on the edge. Okay? So if the circle contains two boys, well, I know this person is not sitting next to two boys, but I know that they are sitting next to one boy. So that means the person right here has to be a girl. Right? And now I want to know, so this girl is sitting next to one boy, and we've assumed that nobody is sitting next to two boys, so that means here there has to be another girl on the other side, and then possibly, well, so this, everybody's sitting next to at least one boy, right? Everybody's actually sitting next to exactly one boy. So I have a girl here, and there's a girl on that side, so there has to be another boy on the next side. Okay? So in between these, so here I've assumed that this circle has two boys in it instead of one. And then in between, I have two girls and then another boy. So in between these two circles, I have girl, girl. Right? So now, what about a circle that just has one boy in it? Well, if it just has one boy in it, since I split at the girls, that means that the people are on both sides, they have to be girls. But now I look over here, this girl is sitting next to one boy, so that means the person over on the other side has to be a girl. But then this girl has to be sitting next to some boy, so the next circle is right there. Okay. So, so roughly, we just argued that each circle contains either one boy or two boys, but it doesn't matter whether it contains one boy or two boy, as because the buffer in between the next group of boys has to be exactly two girls. Okay. So, if I divide the circle up into the table up into circles where the boys are sitting and have the girls splitting those circles apart from each other, then I just argued, using this fact, that in between each pair of circles is exactly two girls. Okay? So, well, if in between each pair of circles I have exactly two girls, that means that overall there's an even number of girls. Okay? So take the number of circles, multiply it by 2, that's the number of girls. But here we have 25 girls, 25 boys. It's not possible to have an even number of girls, and we're done.